Today, we're going to be doing some, collecting some data on you all. So we need some, we're going to be doing statistics, so we need data. So I will talk a bit and then we're going to stop. We won't be going to the computer lab. We'll be here and I want to collect some data on you. So I'll talk about that later. See if that's going to work. Is that off now? Maybe I'm just pushing, I push it too often, I think. Okay. Let's find 20 people. So you four, and you four, and you three, and you four, that's 15, and you four, what's that? 19. And I'll cheat and have you three. Can you all choose a number between 1 and 100? Your own number. Don't tell anybody. Write it down on a piece of paper, but don't tell anybody. In fact, everybody do it, but I'll only ask these 20 people. Everyone, just write down a number, any number between 1 and 100. Your own private number. Don't tell anybody. Okay. And I'm going to ask 20 people, and I will find that 2 of them have written the same number. Absolutely certain. Okay, we'll work along. Have you all done it? Have you done your number? Don't show anybody. Right, you've all done it. Everyone written their number. Private. Don't talk. Okay. Could you, if we shout at the number, I'm only looking at these 20, but everyone, if you hear your number, say. And your number is?
13.
13. We got anybody there? And 5. Nobody got 13 or 5? Whoa, that's good. Yeah? 11. Anybody got 11? 30. Oh, somebody must have 30. Now, you're not cheating, are you? You are going to be honest. Yeah, come on, right. 27. Oh dear, am I going to lose? Yep. 55. Yes? 92. Whoa. And yours? 86. Are you cheating? Yeah, and sorry? 23. Yes. Yeah, and she was in the group. Cool, I won. Yes, yay. 23, 2 23s. Very good. We'll go along a little bit further. But look, that happened. In those 20 people, 2 choose the same number. And yours, okay? 97. 57. Whoa. 15. Somebody must have chosen 15. Yeah? 12. 7. Yes. Yeah. Absolutely reliable. 3 7s. There's always 7s. People always choose 7. That. So in our group of 20, we've got 1 double and one 3. Yes? 100. So 100. 100. Nobody chose 100. 21. 8. 17. And we know all yours. 7, 23. And you? 28. Right, okay. I won't go through all the things. The point is that this is a great game to play with. I play it with groups of kids in schools. You just get 20 of them, get them to choose a number, and they always will choose the same. 2 people will choose the same number. Even though they're choosing out of 100, 2 will choose the same number. And because there's an 87% chance that even if they pick at random, 2 will pick the same number. It's not very intuitive. And of course, people don't pick at random. They pick 7. So that's, okay. So there's a good way, if you're at a very boring party with 20 people, it's a good game to play. Okay, have we still not got this working? Sorry? We're waiting. It's probably because I was pushing the button so often. Oh, well, I hope I haven't broken it. Okay. Now, the other one was on the binomial. We were throwing a dice 6 times. So we're doing 6 throws of a dice, and we're counting what the number was, whether it was 1, not kind of 0, 3, 4, 5, 6, or 2, or something like that, and whether, how many 6s occur. And the point is that the number of 6s, x, has got, what distribution does it have? It's got binomial distribution with parameters, the n equals 6, and the p equals 1/6. Yeah. So the formula for it is there's n factorial over, what do we, x factorial 6 minus x factorial, 1/6 to the x and 5/6 to the 6 minus x. So that's the probability, so we can calculate that. But we can also get SciPy to do this ourselves. And we can get SciPy to simulate from this distribution. In fact, we can get it to simulate 1,000 replications in one command. So pretty well the whole program can be reduced by one command. And then the point is that, and this is why we've got to learn for next week, we're going to have to learn some graphics using matplotlib, because what we want to be able to do is to compare the theoretical distribution, this binomial, which will have look something like, the most likely will be 1. It's going to look something like this, I should think. Very unlikely to be 6 6s, very unlikely. This is probably a bit higher. So it looks something like that. And then we want to compare it with an empirical distribution when we actually do this thousands of times, and we actually get a distribution that will look, well, not exactly the same, but will look a bit like this. We get the actual observed distribution, which won't be exactly the same, but will look like it. And we want to be able to compare those. Okay, so while we're waiting for that to start, we could start on the data collection. Why don't we do this? Yeah. Okay, I was going to do, okay, now, let's start on this. We're going to collect, let's hand those out, Emma. We're going to collect some data. And for 2 reasons. First of all, because to get this idea of a distribution, what is the shape of a distribution? And then we're going to use this data for our statistical analysis. So if you hand out, there's a question, we're handing out a questionnaire. Which I hope will come up at some point. So this is, now, I've tried not to make the questions too personal. And you don't put your name on. So I don't think there's anything too embarrassing here. And you also have got a ruler. You should have a ruler and a questionnaire. Okay. When you've got your ruler and questionnaire, I will go through what I want you to do. Now, this is going to be a bit chaotic. That's fine. Okay. Have you all got the questionnaire? Have you all got that? Yep. And left. What I would like you to do, that looks like that's working. What I would like you to do, whoa, oh, it's gone again. What I would like you to do is to fill this in, and then we can collect it and put the data onto a database to analyze. But not just that, in the class, I want you to actually start drawing some of to come up, and with some chalk, mark in your data. So we can start seeing the distributions, the shape of the distributions. So for example, the first question, so basically when you've done your, try filling in the questions, and when you've finished, come up and take some chalk. So when you finish the questions, come up with your age and just mark your age. Now I've taken it up to 35. I'm up here, of course, so I'm 59, so it's not going to count. I won't put myself into here. It'll mess up the distribution completely if I go in there. But just put, like a cross, and then we can watch how this builds up. Then your birthday, if you just put the month in which you're born, just a little cross there. Now, what distribution should we expect? Yeah, what would we expect this to look like, do you think? Well, the age one. Well, there's no, I don't know if there's anybody 18? No. It'll come up, and then it'll come down, and probably quite a long tail like that. What about the birthday? What do you think that will look like? Well, yes, yeah, exactly. It should be sort of flat, you'd think. It's not for professional sportsmen, in Europe anyway. Professional sportsmen tend to be born at the end of the year, October, November. Now, why would that? Well, yeah, it's true. Why do you think that is? It's to do with the school year. Starts in September. It's because they're always they're the oldest in the class, and therefore they have a big advantage in all the sports that they play, because the sports are played by years. Anyway, so there's another thing. Then mark in whether you're male or female. How many brothers and sisters you've got? What sort of shape might we expect? That I don't know. Probably not really. I don't know quite. I don't know. No, just together. Brothers, sisters together. Any sibling. Brother, sister together. Oh, what your height is in centimeters. If you only know it in feet and inches, you'll have to convert it somehow. I don't know mine in centimeters, but it's easier to do it in centimeters. So you'll have to get out a calculator or your phone and work out what your height is in centimeters. So that, okay. Next is, now we need the ruler. Your hand span. What your hand, you stretch your fingers. How many centimeters that is. And put it in millimeters as well. Millimeters are hand span. And put that up there. I'd put between 15 and 30 centimeters. So I don't know what that will look like either. Don't hurt yourself, don't I? Okay. Oh, this is the other one. I haven't marked it. How long your feet are. Now, they may be bigger than the ruler. You might have to put rulers together. The point is that we can then examine the relationship between feet and height and hand. We can look at this later on. We'll study correlations and things like that. And I'm not sure what units to use on. I'll go back and put this on. Now this is the one this is maybe a bit dangerous. I thought, how long can you hold your breath for? Now, I don't want anyone to die. Don't die. Don't hurt yourself. But I thought that'd be one where I find it very difficult to know what this will look like. So we could try that. Okay, this is a nice one. When you fold your arms, which arm is on top? And do it naturally. You can't think about it. You just have to do it naturally. So my left arm is on top. Your right arm, your right, left, right. Okay, so just look at that and put that down whether your left or right arm is on top. This is the tongue. Can you roll your tongue? It's a well-known genetic... yeah, great, cool. So, can you roll your tongue? It's not, if you can't, it doesn't matter. You're not going to fail the exam if you can't roll your tongue. Okay. Two final ones. I'm going to give out dice. You've got to just Keep on throwing the dice until you get a 6, and count how many times you have to do it. I'm keeping on 4, 5, 6, 7, 8, oh dear, 9, 10, 10. Okay, 10. So I would put a 10 there. I've gone up to 20, but you may go further. Write it in if you go any further. Okay, and the other one, now this is the one skill. How many beans are in there? I don't know, I haven't counted them. So you've got to look, don't open the top. Don't open the top, you've got to guess how many beans are in there. You can look at it, you can sort of measure it, you can do it. You can't open the top. How many beans are in there? So I've maybe given some, maybe this is too much guidance, but I've gone from 0, 500 to 100, 200, 300, 400, 600, up to 1400. Now, try to make your guess before you see what people do, so you don't want you all following each other. Try to do it. So this is a tricky one, and I don't know, but we will find out, and there will be a prize for the person with the closest guess. Of course, the prize might be the beans. But I shall try, great prize here. I shall try to think of something better. So, and on the other side, this is one to do with left-handed or right-handed, because it's not just as simple as are you right-handed or left-handed. I've asked in more detail about different things. What do you write with, you draw with, you throw with, use scissors with, brush your teeth with, use a knife. If you were just using it without a fork, you're just using a knife. What would you use a spoon with? With a broom, if you use a broom, which hand do you put at the top with the broom? If you strike a match, which hand holds the match? And if you open a box, which hand holds the lid? Well, I could have put which leg do you? Yes, I should have done that. Which leg do you use? Yeah, yes. No, I didn't think of that. Which leg do you use? Yeah. Actually, we could put that in as an extra question. Actually, I should put that in as an extra question about which to do. And then there's a way of calculating a score at the bottom. So essentially, you put a plus if you use that hand, and a double plus if you only ever use that hand. And you can put a plus in both columns if you use both. Okay, so this will take a while, but this is valuable data. The other thing I've asked is that, and this is not to be handed in really, can you write down on a piece of paper what you guess these distributions are going to look like? Really think about it. Some of like this one we expect, it shouldn't have any pattern. And we know the male and female, but the tongues, what proportion do you think are yes and no? Okay, is that clear? Are there any questions?
We need dice.
Oh yeah, you need dice, yeah. Well, hand round, and the rulers, you should have rulers round there. I'll come round and hand out a dice for each. There should be a couple, one or two for each table.
Yeah, there should be spare form.
Okay. Emil, can you pass? Oh yeah, thanks. Great. You pass one to the back. Yeah, great. Okay, who wants to start with this? Start guessing. You can weigh it, I suppose. How long are feet? 20. Who's got the smallest feet? Have you got small feet?
No, I have big feet.
Who's got small?
Brenda.
20.
Brenda has small feet.
20 would be about smallness, wouldn't it? Or maybe. I don't know how long feet are. I don't know how long people's feet are. How big are feet? Yeah, okay. Don't hurt yourself. No, look, you can't count them individually. That's yeah, pass around the beans. Keep them going. How do you... Where's your left? Yeah, you have to do it naturally. You have to do it without thinking, because once you get self-conscious, it's difficult to do. Left, yeah. Cool. Hi. Yeah.
Indifference, is it like ambidextrous?
Yes, you could be, if you could be both. You could use either. So a plus in both of them. If you, yeah. If you do calculate your handedness score, you can put it down there as well. So this is completely right-handed, and that's completely left-handed. Yes, if you've got a watch on your phone, yes, yeah. Yeah, if you've got a stopwatch on your phone, it helps. I said, don't die. Yeah. The beans, yes. We'll get the beans in a minute. Okay, she's still looking at the beans. They're being a bit slow on the beans. Come on, you can't hold the beans forever. You've got to pass them on quickly. So if you're finished and waiting for the beans, come and mark some of the data up so we can start seeing it. So as soon as you've got something, if you're just waiting to do the beans, come and mark, start putting some crosses. Come on, start putting some data. We need some data points. I want to start seeing something. Lovely. Just roughly where it is, yeah. It doesn't have to be exact, yeah. Oh, well done. All right. Okay, our first data is arriving. Lovely, thanks. Now, I was going to say, because I was supposed to do the slides on distribution, so for people who've finished, they can do some maths. There's this. I was going to do the stuff on the exponential distribution, and you've got to prove the mean and the variance and find the median. But I haven't done the slides on that yet, so it's a bit tricky. Even if we haven't done it, I've given the form of the distribution up there, so I think you can still work on the mean and the variance for it. Okay. Right. Oh, this is looking good. Yeah, that's it. Start building it up. Yeah.
Now, about the shape, which shape shall we choose?
Which one?
About this question.
Oh, it's really just your judgment. Just drawing, what sort of shapes. Just draw it. Yeah. It's not a mathematical thing. Just a rough feeling of what you think. For example, this height. Is it going to look like that, or will it look like? Will it have two peaks? So what the rough shape it might be. Oh, this is great. I've got to think of a prize now. I don't know. I don't think it's going to be a very big one. What can I do? Now, where are the beans? How are the beans getting on? Are they still going round? They've eaten. Yeah, no, that's why I didn't use jelly beans, because people would start eating them and spoil it. But no one's going to eat these beans. Okay, if you can get the final dots on. How are you getting on? If you haven't done the beans, can you try to make sure you do them by the end of this morning? So, because we really want these pieces of paper to have every bit of information. Because if we have missing data, it makes it more difficult and complicated. So try not to have any missing data. Because next week we're going to be analysing this data. There's a huge amount of statistics here. Okay, have a look at the distributions though. Have a look at the shapes that we're getting and see whether they're what you would expect. See what sort of shapes we're getting and whether they fit what we would expect. Because we're going to have to, for these data, we're going to have to fit probability distributions. We're going to have to put these into mathematical models. And some of them should be fairly straightforward, and some of them are going to be quite tricky, I think. Okay, let's look at this one first of all. How many throws to get a 6? So what we got, looks like it's sort of coming down like this. What is the name of the distribution that this should obey? Do you remember we did it? What was it called? No. It's the waiting time till the first. It's not how many 6s. It's the geometric distribution. Thank you. Yes, it's the geometric distribution, and so which obeys one. Remember, it's 1 minus p to the x minus 1 times p, the probability that x equals x. Now, what is p in this case? A 6. Yeah. So it's 5/6 to the x minus 1 times 1/6. So, in a way, so that means the first one is, how high should this be? What proportion should be in here? If I put x equals 1 in there, what do I get? I get 1/6. So this should be 1/6 of the observations go into this one. And how many? Well, we got 9 in there out of 50 something. Dead on. Lovely, just what we would expect. We would expect 1 in 6 of you to get a 6 the very first time, and it happened. Great. It's not always going to work so well. Now, how many should be in the second column? If we put x equals 2 in there, what do we get? 5/36. Yeah, we get, which is slightly less than 1/6, not much less. It's only 1/36, so this is almost as big, but not quite. And what about the third column? When x equals 3. Yeah, 25 over 6 cubed, which is 216, that's it. Now these, if we draw this, it'll actually look like something like that. It goes down very slowly. The peak is here, goes down very slowly like that. And that's pretty well what we're getting. This is somebody waited till 20, but that's not, I don't think, either they were cheating, or, which I'm sure is not the case. I'm absolutely, no, this is, I think this is probably quite a plausible result. Well, we can check that next week. We'll actually do a test on whether they were cheating. We can do a stats test. So that's really quite nice. We would expect a shape that looks like that. The highest should be on the first one, then it slowly decreases. So that's really nice. Now, no, this is just guesswork, isn't it? So I don't think I would expect any particular shape for that, because this is judgment. And we'll just see what, some people thought there's a lot. Maybe, did people want to go higher? Maybe people put more than 1,400. There are thousands in there, yeah. Okay, age. Now. Age looks quite nice. A sort of, what's really nice to analyze are nice sort of symmetric distributions like that, because we can assume, usually a normal distribution or some nice assumption. So that's quite nice. No big, but if I was in there, it would ruin it, because you'd have somebody up here, 59. It'd be hopeless. So I won't put, it'll spoil it all if I go in. Now this, should we expect any pattern here? No, I don't think so. But we've only got one in October. Only one October birthday. Do you think there's something special about October? October doesn't produce mathematicians. This is a new discovery. A new Ames theory that people born in October tend not to be mathematicians. Isn't that what a great discovery this is? Or there's an alternative explanation. What's the other explanation? Just September. Sorry? Oh yeah, well September, yes. Yeah, well August, yes, lots in August. August is a fantastic month for mathematicians. But do you think this is serious? Or is it just luck, just chance? Do you think so? We can test it. Next week we'll be testing whether this actually is a proper, there's something there, or whether this is just luck. Because we wouldn't expect an exactly uniform distribution. And there's always, just by chance, it will be, as people were saying, it will look like that. But, if we had hundreds here and nobody in October, that really would be strange. So we'll test whether this is strange. Whether that's just a fact. This is interesting. This varies very much by country. In England, this would look very different. So we got a distribution looks like this with a quite long tail. Well, I referred to the language. I use a tail for a distribution. A tail is something that sticks out. A tail sticks out. So it peaked like that, and so that's an interesting one. We got an 11, which I think that deserves a prize as well. But that's yeah. So that's quite interesting. Yeah. Okay, height. Now height, there seems to be two peaks. Why would there be two peaks for height? Females and males. So one of the things we'd want to do is to split those and then to see what the distribution is between. For height, it's very easy to get things that look like that. And for some other measurements as well. And what we want to do really is to split those, because it's when there's such an obvious factor that predicts things, you should split them up. So that's but we've got nobody up here and nobody way down, nobody down there. Now the hands, this is lovely, because this is really quite smooth, nice smooth curve, not quite symmetric. They've got something really big. Someone's got very big hands. It's enormous. But again, it doesn't look as split as for height. But we can check that again by gender. Foot length. Oh, that's very nice. Lovely distribution. Beautiful distribution. Lovely, nice, smooth curve. Those are the sort of things we like. And breadth as well. Oh, actually, some people diving. These are very useful. Very useful if you're drowning, I suppose. But this is. I hope they didn't hurt them. A minute and a half. I hope nobody hurt themselves. That's very good. That's somebody who can useful for swimming. That is, yeah. And then this way. This is a bit pathetic, to be honest. Don't go swimming. Don't go swimming. This is really, yeah. Again, we can analyze that. Now, we've got, hang on. I'm in the minority. The left is in the minority compared with the right. How interesting. Yeah. Right, okay. And tongues, there's quite a lot can't roll their tongue. Quite a lot. And so we'll see whether that's related to gender, whether it's males and females. We can test all of that. Okay. And the handed score. The interesting thing about this is that you may have predicted that people would be, I would have predicted, that people would be either right-handed or left-handed. And there's a few who are very left-handed. But this is very interesting. There's clearly people who are quite ambidextrous. Now, maybe these people who were left-handed and had been taught to write right-handed. It used to happen a lot, that people got, made to write with their right hand and things like that. So you end up with a mix of things. So that's quite interesting. And we can, I thought we can see how related that is to how you cross your arms. Because there's clearly there's a lot more people who do the left-handed than that. Okay, so this is great data. Thank you so much. This is really good. So we're going to, we want to make sure everyone fills in the beans before they go, has their guess on the beans. And all this data, if we hand in these forms, we'll get these onto a database. So we can start, and that's why we've got to learn some graphics, because I really want to be able to, we can't leave these up all the time. We want to get on and do some, be able to plot these and analyze them and test some hypotheses. The October hypothesis for mathematicians. This is the science we've got to do. And think of other things. I don't know, what else could we check? What else is interesting that we could look at on these? Any ideas? Yeah, sorry.
The relationship between the handspan and foot length.
Yes, yeah. And height, I think, as well. Yeah, exactly. You would sort of think that if we did hand here and foot there, what do you think they would look like? We might think that there would be some kind of correlation. So we can measure that. Not an exact straight line, but we think it quite unlikely that somebody has got tiny little hands and huge feet. Or vice versa, tiny little feet and huge hands. Yeah. Now that would be, hang on, tiny foot and huge. Yeah, that's small feet and huge hands, and that's tiny hands and big feet. Okay. So we expect them to be there. So I think it'd probably be quite a high correlation. Maybe 0.8, 0.9. I don't know. We could check all that. Any other things we can look at? And we might want to do this by gender as well, separately for males and females. Right, okay. Well, we still can't do anything with this. So what I'm going to do one more thing that I want you to do, which I was going to do, and then we'll catch up. I hope this is mended tomorrow with the lecture. Okay, the next thing, the thing on my lecture notes, which are on the, you can still look at them, they're on the website, was something called the central limit theorem. Now, who is that familiar to? I'm not going to test you on it. Is that familiar to people? Yes, I thought it would be to you. Yes, some people. It's a nice idea. It says that if xi is some random variable with any distribution, so it could have a distribution shaped like this or like that or like anything. If I take a whole lot of these, add them up and take the average, and I'm going to write that as x bar I'm going to call that, the average of them, then this x bar has got, for n big enough, as n goes to infinity, x bar has got a normal distribution. It's got a normal distribution with variance, roughly speaking, mu and sigma squared over n, where mu is the expectation of xi, and sigma squared is the variance of xi. Now, I mean, it's quite remarkable, really. It means that if we ever take an average of anything, those averages will tend to form a nice normal distribution. And remember, although we haven't done it yet, normal distributions are ones that look like that, which was the slides I was going to use. These are normal distributions, also known as Gaussian distributions. Beautiful things, which we're going to use a lot. And they are shaped like, roughly, yeah, that's not bad, that's quite good. That looks pretty good. This looks, well, if you took those off, that would look pretty good. You know, sort of bell, like a bell. Sorry? Like a what? A bell, yeah, a bell shape. Bell-shaped curve, they're also known as the bells. And they do happen. We can see they really do occur. They often occur in natural phenomena. People's heights, beautiful shape usually. Okay, so that means it's normally distributed, whatever the shape. And I want to test that. I'm going to test that now. Okay, now how am I going to test it? Okay, I'm going to do something. Yeah, yeah. It's the expectation of xi. Yeah, of each of these xi's. So it will also be, this is also, and I did this, the expectation of x bar. Yeah. Okay, now, this is a test I want you to do. What I want you to do now is I want to demonstrate the central limit theorem with uniformly distributed random variables. And what I'm going to do is pretend you are the South African National Lottery. Okay, so the South of the lottery, you pick 6 numbers from 1 to 49. Now, the lottery picks them without replacement. We can do it either with or with. We'll do it with replacement, slightly differently. So xi is equally likely to be 1 up to 49. And it's got a uniform distribution. It can be any one of these numbers. And then we're going to calculate x bar, which is x1 plus x6 over 6. So we're going to pick 6 lottery numbers and take their average. And I'm going to want to get each table to pick 6 lottery numbers and take their average. Now the numbers will be uniform. You know, it could be equally likely to be any number between 1 and 49. But the average of those numbers, when we look across the tables, will, I hope, will have something like a normal distribution. Now, here is the challenge to you. With the technology that you have with you, how are you going to pick a random number between 1 and 49? Without going onto a computer and using a random number generator, or having balls, because I haven't got any lottery balls. I got them at home, but all without home. But how can you pick a random number? How do you think you could do it? Any ideas? Because picking random, you can't just think of them. That's really, like, if you think of them, we'll end up with 7. We know people are very difficult to think. So how can you choose a number completely at random? One number that is equally likely to be 1 to 49. So like 43 or 6 or something like that. So it's like putting your hand in and pulling out one number. How could you do that? For example, people have suggested things like getting a thick book and flipping it and then sticking your finger in a page and reading off the last 2 digits of the page number. And if they're between 1 and 49, using that number, and if they're not, doing it again. So that would just be, you need a really thick book, you flip and stick your finger in, and there's a random. Okay, we haven't got thick books. How do you think you could do it? We need a random, if we had random number tables, because there are published tables, you go onto the web, and there'll be published tables, you can just stick your finger in and pick, and it'll give you the numbers. If we haven't got random number tables, how do you think we can do it? Any ideas? Yeah, no, without a computer. No computer. You might use some other technology, or you could get little tickets, write 1 to 49 on them, and stick your hand in. Okay, so you could do that. So you could like imitate a lottery. Any other ideas how you might do it? Yeah? Oh yeah, but some letters are more common than others. No, I like that, because that's nice, but the problem is the letters are not equally common. So if you did, certainly in English, E is the most common letter, and so you'd pick number 5 all the time. But I don't know if letters would work. Any other ideas? No, that's nice. Yes, you could represent the numbers in binary, because you can get a random binary sequence by I never thought of that, by flipping a coin. So we know by flipping a coin we can get a random sequence of 0s and 1s. And then if we took, how many for binary, to go up to 40, 64 is, that's 6 of them, isn't it? If you did the first 6, you get a number between 1 and 64. And then you just throw out the ones that are above 49. God, that's good. That's quite good, isn't it? Yeah, I didn't think of that one. Right, okay, well we could do that. What about, okay, I've got another method, I think. I don't know if this is good or not. Actually, I don't know if it's good. Oh, I haven't got, any money. Hang on, just a moment. Yeah. This is one I had, but I don't know if it's good. Take a note. It's a 10 rand note. And look at the last 2 figures in the number. Every note's got a number on it. 57. Actually, that's useless because it's not 1 to 49, is it? But you'd have to go through lots of notes. But do you think that's good? Do you think that's reliable? Yeah, I mean, you don't know how they put the numbers on the notes, really. That's one of the problems. I thought, what about this, of going through your friends on your mobile phone numbers and using the last 2 digits of the mobile phone numbers. Do you think that's work? Do you think that would work? If you went through your mobile phone number and just used the last 2 digits, because you don't know how these numbers have been allocated, but you'd hope that they are the last 2 anyway. You couldn't just use the first ones because you'd just have 07, you'd have whatever the code was, or it'd be useless. But the last 2, I think, might work. Okay, so what I want you to do, could each table generate 6 numbers? 6 lottery numbers between 1 and 49. Either by the phone method or some other, actually we haven't got books, or this agents method, which is essentially what one does is flip a coin. The best way to think of it perhaps is you flip a coin and you go 1 to 32 or 33 to 64. If it's heads, if it's is this right? And that's 1 to 16, and that's 17 to 32. Yeah, and that would be like working down this binary sequence. Does that make sense? You'd have to, you'd sort of, and then you'd end up, after 6 flips, you end up at one number. If you end up above 49, you just have to do it again. Yeah, okay, so what I'll say is just flip a coin 6 times, get the binary sequence, and then turn this into a number. Exactly. Where that is 1, that is the 2s, that's 4, 8, 16, and 32. That's the easiest one. Okay, so just flip. If you use this method, or I thought I like the mobile phone method, but never mind. That's because I didn't think of this. Okay, and then when you've done 6 of them on a table, take their average. All right. Okay, go. Have a go at that. So you need a coin or a dice or something like that. So each table gets 6 numbers between 1 and 49. The way I've written it up there, a head is 1, tail is 0. So if you've got head, head, tail, head, it'll be 1, 1, 0, 1, 0, 1. So that'll be 1 plus 2 plus 8 plus 32, which is 43. But you may have used head or tail the other way around. You're using the mobile phone? Oh, you've got a dice with how many sides? Oh yes, you're okay, you can do more sides. I have got one with 49 sides, but it's I didn't bring it, yeah. Okay, when you've got your 6 numbers, take their average. Take the average of the 6 numbers. Just add them up, and so just add up the 6 numbers and divide by 6. Just for those 6, just a simple thing. Simple average of the 6 numbers. So when you've got your average, have anyone got an average they could tell me? Yeah, okay. Actually, first of all, I won't write down all the numbers you've done, but can you give me your 6 numbers? What are they? 8, 6, 9, 23, and what, sorry? And 15. Okay. And 25. Can you give me your 6 numbers? Sorry? You can't have 0. It's got to be between 1 and 49. No, if you've got 0, you've got to throw it out and do it again. Sorry, yeah. Yeah. Sorry? 2, 20, 17, 21, 15, and 42. Good, I'm glad we got some big ones. Any more? Yes, shout them out. 34. What, sorry? 30, 42, 10, 29, 15. Lots of 15s. Okay, I think, if I ask everybody, if people have done this correctly, they should end up with an even distribution. So this should be a uniform distribution. Now, and this is the test, what are your averages? What is your average? 16. That's quite low. Okay, 16 for an average. Oops. Go on. Okay, anybody else got an average? 27. That's what I like to see. 27. Sorry? 21. 22.8, right? Any more averages? 11. As an average. You must have got... Did you do this right? You're going to spoil my example if you're not careful. Did you? Well, maybe I'll put a little note. If you use the mobile phone method, it might not be such a good method. Maybe people don't use big numbers, yeah. Any more got an average? Sorry? 11 as well. Did you use the mobile phone? No. 27, great. That's what I want. Sorry? 22. Okay. 22 there. Any more? Sorry? Which one? 31. 31. Good. Any more? 43. As an average. No, no, I want the average. No, I don't believe you've got an average, because you'd have had to have 6 numbers all around 43. That's very unlikely. Okay, any more averages? 21. Okay. 20. Sorry? 18. Oh dear. It's a bit low. Right. 3. That's not an average. You didn't get an average of 3. I refuse to believe that. Yeah, I refuse to believe it. Sorry? 32. Lovely. Right. Okay. Okay, can we stop? Peace. Shush. The mean. Have you got the mean? It's just the mean. Right. 27. Great. That's what I wanted. 27. Lovely. Now, what I was hoping for is the fact that when you take an average of these, what we're getting is they're much more concentrated around the midpoint, which is 25. That's the midpoint. So the individual numbers are scattered over the whole distribution, but the averages tend to, apart from this strange ones, which I don't believe, the average are really classified. What I was expecting was lots around 24, 25, 26, 27, 23, 24. Averages like that. And if you'd done it instead of 6 numbers, you'd done 10 numbers or 12 numbers, they would have been really tight around here. And also, they would form a nice normal distribution like that. It's quite remarkable that, and it didn't matter, although the original numbers come from a uniform distribution, the averages start focusing. And it's sort of intuitive, isn't it, that it would be very strange to get an average out here. It's not strange to get a number 48, but to get an average of 48 would be really, really strange. So this is absolutely fundamental. It's a really important thing to demonstrate. The fact that, but it's actually something that it's quite difficult to grasp. You have to distinguish between sampling from a distribution, the actual numbers, in which case it would be like sampling from here. If I picked one of you, it would be like sampling from one of these distributions, and they would have whatever shape they have. But if I sample averages, it loses memory of what the original distribution was. The averages start having this normal distribution, become very focused and tight, much less variability. And this is important. So if I took a group of you, if I took 6 of you and measured your average hand span, and then took another 6 and measured their average hand span, the distribution wouldn't look like this, it would look like that. It'd be much more focused around the middle. Tight. So it's something we use all the time, because what it does is give us an excuse to assume normal distributions for averages, even though the original data didn't have a normal distribution. So I hope I demonstrated, I hope you demonstrated that. The averages are very stable, even if the original numbers are all over the place, are everywhere. Okay, well, I think I've run out of things to do now. Can I ask you, since we didn't have the slides, my slides are up there, are on the website. Could you have a look at them so that tomorrow we can go through them quite quickly? They're not, basically the slides talk about, and I can talk about it a bit. Actually, I'm not going to rub these off because I want to take photographs of them. Basically, the slides talk about continuous distributions, which we're seeing, which is things like normal distribution and an exponential distribution, which is just the continuous version of a geometric distribution. It's the same thing. So these, and we're going to be doing lots more distributions, but these are continuous. They cover the whole, well, this one covers the whole real line. This one goes from 0 to infinity. And they've got derivatives. They're continuous distributions with derivatives. And really that's what that and this central limit theorem is what the lecture was about. So I think I'll just leave it now, but please have a look at the slides before tomorrow. Okay, are there any questions? All right. Oh, just make them up. It's because people, if I ask you to choose a random number, it's very difficult to choose a random number. People will usually not choose 10, 20, 30, 40. Exactly. If when people choose a number, it doesn't follow the correct mathematical distribution. That's why you need to have a mechanical means to produce these random numbers. Because people have favorite numbers like 7 and avoid things, yeah. So you could try making them up, but what people tend to do then is to choose them so they're equally spaced. They will choose 7, then they want, so they tend to spread them out too much. Actually, we might do that. Actually, we got time to do one more thing. Yes. Can I do one more thing then? We're all right, we've got time for lunch, haven't we? Yeah, okay. What I want you to do is get a piece of paper, and this relates to what you said. Get a piece of paper and pretend that, get a small piece and tear it into a strip. Tear 2 strips of paper. Tear 2 strips of paper like that. Tear 2 strips of paper. Now what I want you to do on the first one is to invent 20 coin tosses. So just sit and invent them. So just go heads, tails, whatever. So just write heads and tails 20 times, a row of 20, but make them up. Don't toss a coin. Just make them up. So pretend you're a coin. Pretend you're a coin and say, okay, I think it's going to be heads, it's going to be tails. So just write 20 heads and tails, which you make up. And just sit and do that now. And have it on a separate piece of paper. Have it a piece of paper on its own. It can be any, it doesn't have to be a small strip, it could be any size, but just have it on a piece of paper. Okay, now when you've done that, what I want you to do now is to get a coin and do the same thing with real heads and tails, a real flip. So do 20, so actually flip a coin and do heads, tails, 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 heads, heads. So do a sequence of 20 real flips. Has everybody got a coin? If you haven't got a coin, borrow a coin from somebody. So I haven't got one any on me. Oh, I have. If people have got I've got some coins. Can I have my coins back? Yeah. Do you need a coin? Okay. I need it back. I need it back. No, I want my money back. I want my money back. I haven't got one. You could throw a dice and make 1, 2, or 3 equals a head, and 3, 4, 5 equals 4, 5, 6. equals a tail. So if you don't have a coin, use a dice. Smile, smile. Okay. Now, when you've done that, you should have two pieces of paper. Now, turn them over, and on the back of them, very lightly, don't press too hard, could you just write real, if it's the real sequence, or pretend, right, pretend, if it's the pretend sequence. But write it on the back very lightly, just faintly in pencil or so don't push. So you don't want to be able to read it from the other side of the paper. So just write pretend on the back of the piece of paper. Not because it's going to be we're going to do this as a quiz, a challenge. So to write it on the back, so you need two pieces of paper. Two separate pieces of paper. So you should have two pieces of paper, one real and one pretend, and with it written on the back very lightly. Okay, now, is that all right? Still going on the numbers. What you do then is, if you're on a table, put all your pieces of paper together in the middle, but face up, so you can't see. No, the other way. So with the results upwards, so you can't see whether they're real or pretend, and mix them all up. Because what you're going to do then is pass them to another table, and they're going to try to guess which ones are real and which ones are pretend sequences. That's the point. It's a game to see if you can guess. So put the pieces of paper together on top, so that you can't see which ones are the real and which ones are the pretend sequences. So that's a secret. Okay, great. Now, when you've done that, pass it to the table, pass them to a different table. So swap one table, just find the table next to you and swap yours. But make sure they can't see whether they're real or pretend. And then when you get the ones from the other table, spread them out and try to guess. Try to put them into two piles. The ones that are real and the ones that are pretend. And don't cheat. Don't look over the paper. Do not cheat. So that's what you've got to try to do. You've got to try to guess which ones were the real and which ones were the pretend. Okay? So no cheating, no cheating. So you write it on the back. All right? If you've done that, and then you can give them to the table behind. And no cheat. So what you do when you get them from another table, don't turn them over, don't cheat. Just try to guess. Have a look at them, and try to guess which ones are the real and which are the pretend. See if you can spot differences, but don't turn them over. Don't cheat. Okay, have you passed them over? Yeah, give them to the other table. Oh, the coins, yeah. Coins, money. Anyone got any money? Money. Anyone got any money to give me back? Oh, thank you. Great, thank you. Okay, have you done that? Have you given them, so are these theirs? So are these yours or their? Are these your ones? You swapped them. Okay, now you have to guess which is a real and which is a pretend sequence. So you have to look at them and guess which one is real and which one is pretend. And see if you can guess which one. Just look at the pattern. Okay, now just look at them and see if you can tell
Which one is real?
which one is which real, just by looking at the sequence.
Can choose.
Which one's, and how would you tell them apart?
This one is
Rit.
There is a Rit. This is the one real.
Right, yeah?
This one is
Pretended.
No, I think that's the real one.
This is real.
I think that's the real one.
Me too, I think it's that one.
Why do you think that's the
There is
real?
a real.
Why do you think so? I think that's the real.
That's the real.
Why do you think so?
Wait. No, I don't think. This
Oh, no. That's the real one. That's the real one.
the same as okay, real.
I guess. Yeah, what do you think? Okay, how are you getting on? Don't cheat. Okay, let's pause a moment. How are you trying to choose? How are you trying to separate which is real and which is fake? What kind of things you might, what kind of strange pattern? Shh. Yeah. So if you see tail 4 times, which one do you think it is? It's the real one. Exactly. If you see head 4 times, it's almost certain to be the real one. Now, why is that? Why do you think that's the case?
You tend to alternate.
Yeah. Come on, why do you think it is? Why do you think it is? Exactly. You tend to do very short sequences. I bet when people were inventing them, I'm fairly confident probably almost nobody put even 3 in a row. But, sorry? You got strange kids because normally, that's quite tricky, those. There's no long sequences. Yeah. Oh, no, that's quite tricky. Okay, so the usual thing to look for is long sequences, because if you flip a coin 20 times, there's a very good chance you will get 4 in a row. And you're almost certain to get 3 in a row. And I've forgotten what the probability is to get 4 in a row. You can write a simulation program. Anyone who's interested can do it. It's a good chance of getting 4 in a row. So, knowing that, can you separate them? Okay, now turn them over and see if you're right. Have you checked whether you're right or not? If you turn them over, were you right? Check whether you got whether you were right or not. Okay, did you get them right? You did get them right. Cool. Okay, who got them right? Who got them right? You got them right? You got them right? All of them right? Cool, brilliant. Okay. Who got most of them right? 3 out of 4 or something like that? Yes, yeah. You can't always do it. Who got it completely wrong? Hey! Could you spot them?
This one is
That's real. There's 4 H's. 4 H's, so that would be real, wouldn't it? Yep, exactly. Good. All right. So just to stop then, the lesson from that is that truly random sequences do not go head, tail, tail, head. They cluster. Things cluster. It's like the birthdays. You get all these coincidences happen. And so the way to test a fake is if it almost looks too random. And this is a very reliable test that you can use to see if someone's inventing something, and that's why you can't invent random numbers. That trying to be random is really difficult. Okay, well, we've managed to fill in 2 hours without without a projector. So thank you all very much for joining in. Let's have some lunch. Oh yeah, those forms. Make sure you filled in everything and give them to some of the tutors, and because we'll need those for next week. Oh, dice, money, forms. So we don't know the result yet. And somebody has got to count. Has everyone done the beans? Has everyone guessed the beans? Because somebody now has to count the beans. It's somebody, I don't know who's going to count the beans.